All right, class, here is section 1.3, library of functions, and then piecewise defined functions. So, as I said, first we're talking about functions in general, and then we are going to concentrate slowly on specific functions, starting with the easiest kinds, and then on and on we go. So, as a visual, it is important for us to know what the graph of our specific functions is going to look like. So here are the easiest, most basic type of function. This is what I mean. Now, a constant function is really nothing but f of x equals to 2. As you see, for example, in this first example, there is no x in the equation of this function. So this equation here is really nothing but the equation y equals to 2. So no matter what, all the y's are going to be 2. No matter what the x's are, all the y coordinates of these points are 2. So a constant function is the easiest type of function because nothing happens. Y, where the function is constantly equal to 2, nothing can change it. Okay, so the graphs of constant functions, as you see, are going to be horizontal lines, right? Y equals to 2. The identity function, f of x equals to x, or in other words, y is x. No matter what x is, y is the same. So this equation here, or this graph here is going to go through what points? 0, 0, x is 0, y is 0, 1, 1, x is 1, y is 1, 2, 2, 3, 3, 4, 4, 1.5, 1.5, yes, so on and so on. So the identity, or the y equals to x line, is really the most basic linear function. Any other linear function that we'll be discussing in the next chapter, so something like, let's say, y equals to 2x plus 7, that's also a linear function. It has the same shape. Okay, so any other linear function has the shape of this identity function. Absolute value functions will be the next one. So any other function that we'll be discussing in that section, say f of x is the absolute value of x minus 3 plus 2, something like that. That's an absolute value function. It will have the same shape as just absolute value of x. So this is the most basic absolute value function. Nothing else is happening to x, but we're taking an absolute value of it. So as you see, it has this V shape. Okay, so hopefully now you understand what I'm trying to tell you, that as we would move on section by section, we'll discuss absolute value functions. We expect a V-shaped graph. We're discussing linear functions, something x only, times the number, but no square roots, no squares, no absolute values, nothing else happening to x, but plus something or times a number, then there's that. Quadratic functions, their shape is a parabola. Cubic functions, their shape is almost like a broken parabola, but this part goes down instead of stays on the same side. So anything that's a third power, 5x cubed minus 3x, something like that, will look like this shape. The square root function, remember how I said the domain of the square root function starts at 0 and goes to infinity? This graph is not even on the left side. So by the way, let's look at what the domain of all these functions are. The domain is all real numbers. These graphs are stretching all the way left and all the way right. Yes, negative infinity to positive infinity, negative infinity to positive infinity. Same thing here. The domain is all real numbers because the graph will slowly but surely go all the way left and right. Same thing here. The first graph that does not go all the way left and right is the square root function that we discussed in the last section. That graph only starts at 0 and goes to infinity. Okay. Cube root, as you see, you can take cube roots of negative numbers. Test it with your calculator. Totally possible. So that graph, this graph of the cube root function does not stop at 0. It goes all the way down to negative infinity. This is another function that gave us trouble in the last section. And as you probably see, this graph is stretching next to the y-axis, jumps over it and stretches next to the y-axis. Definitely this graph skips over x equals to 0. It does not cross the y-axis. So it has no point on this graph where x is 0, right? So again, the domain is, I'm going from negative infinity all the way to 0, not including it. So that's this piece right here, up to close as possible to 0, but not including it. And then skipping over 0 and starting on the positive side. Same thing here. 0, if I plug in a 0 here, 0 squared is still going to be 0. I cannot divide by 0. And as you see, this graph also does not cross through the y-axis, but skips right over it. Okay. So these are, just wanted to give you a visual. Get used to these graphs. You see something with x squared, you expect this shape. You see something with just an x, you expect this shape. You see something with an absolute value, you expect the absolute value shape. So get used to these shapes, because as I said, when we graph a function, let's say we would need to graph f of x, or look at this function, the absolute value of x minus 3 times 2 plus 7, I definitely expect some v-shaped out of this graph, right? I see a function that says f of x is 3x squared minus 1. I expect this kind of shape. So if we know what the shape looks like, then we don't need to find and plot 100 points just to see what happens. We just need a few key points in this graph, and then I would know how to graph the rest of the function. So it saves us a lot of time if we know what we are dealing with. Okay. All right. So I'm going to delete this and move on. I'm keeping these sections super straightforward and super short. So here it is. That's the library of functions I want you to get used to. Now, a piecewise defined function is simply a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all these smaller domains. So we'll see what this means. It might sound a bit complicated, but I will make it sure you understand. So, for example, the absolute value function is a piecewise defined function. So the absolute value of a number is the number itself, right? If those numbers are more than or equal to 0. So as soon as we put a number that's positive in here or 0, it stays the same. However, as soon as you put a number that is less than 0, yes, what do you have to do with this number x? You have to take its opposite to make it back positive, yes? So you have to take the opposite of this number x. So therefore, the absolute value is itself x if x is greater than or equal to 0, and negative x if x is less than 0, right? So that's the definition of the absolute value. So here it is. I'm giving you, think about the functions above. I'm just giving you straight up basic functions, not making them too complicated. But let's see what this means. It says, if x's are less than 0, so on this side of the graph, I want you to just graph f of x equals to x. So if you remember from up above, f of x equals to x is this line, yes? That goes through 0, 0, 1, 1, negative and so on and so on. But this definition, this is f of x equals to x. But this definition here, f of x equals to x, says just grab this piece of it up until x is 0, and that's it. Do not go on. Okay, so the point is its own pieces only. So only for x is less than 0. For x is greater than or equal to 0, so on this side of the graph, grab the square root function. So if you look at the square root function, it looks like this. It's like a sideways parabola. And that's it. And they meet at 0, so we continue right through. Right? So if I plug in a 0 for x here, I get 0. Square root of 0 is 0. So both pieces end in the same spot. Now, let's try this one. The break in this function is that just to make sure we see it, it's not part of the graph, but these graphs are going to look somehow up to x equals -2, somehow between -2 and 3, and somehow from 3 on. Okay, so up until -2, I have the horizontal line y equals to 5. So it's a constant function, all the y's are the same, and that y is 5. Between -2 and 3, I'm grabbing the x squared, the parabola function. Now, see how here at -2, these two graphs don't meet? So I'm not continuing in the same point. That means I have to tell you which point is included. So the -2 is included here with 5. So I'm going to put a bubble, close bubble, but not here. So I'm going to put an empty circle. So in other words, I need to know when x is -2, on which part of the graph do I grab, right? So in other words, what is the corresponding y value when x is -2? Remember, this is a function. So when I plug in this function, the value -2, I should know which piece of the graph I'm at. So when x is exactly -2 equals -2, I have to grab this definition of the function, so 5. Okay. And this is going to go on to an x is 3. Let's plug this in. What is f of 3? So if x equals to 3, I'm on this part of the definition. 3 squared equals to 9, by the way. So when x is 3, 6, 7, 8, 9. So this is going to go as high as 9. Okay. All right, fine. And after 3, it's x. So be careful. 0, 0, 1, 1, 2, 2, 3, 3, and so on. So it's the line, but only after 3. Same thing. The bubbled in point was up here with the parabola, with the x squared function, right? And now with the x. So when x is equal to 3, I have to use the x squared definition. So be careful. With piecewise defined function look differently on different parts of the number line. So even though I've given you our basic functions, you need to grab the piece of them, right, that corresponds. So let's say more than 3, we only grab this part of the line, right? Between -2 and 3, we only grab this piece of the parabola, right, and so on. Okay, let's try this again. Here. Same thing, I just want to give you basic functions, but they switch definitions at -3 and at 0. Okay. One way you can do this, remember the absolute value function was this? The v. Oops. Trying to make it go through the corners. There you go. Okay. So we only want this function up to -3. So we only want to keep it up until this point. The rest of it has to be deleted. All right. So only up to here. I'm grabbing the absolute value function only up to -3. Between -3 and 0, it's the horizontal line y equals to 2. And both these ends I'm going to bubble in. Both those ends are going to be bubbled in because equals 0 and equals -3 are part of this definition. And for x is greater than 0, I have to grab the reciprocal function to the right of 0. So if you look at the reciprocal function, it looks like this. And I'm only grabbing the piece of it that's to the right of 0. I'm only grabbing the piece of it that's to the right of 0. Okay. And that's the graph. So I'm going to draw a function. So I'm going to go backwards, and we want to write the piecewise, the equation of it. So here I'll draw a function for you. And hopefully it's all about you getting used to those definitions. So what function would this be? Now also it's important that we get used to writing. It's not two different functions. So remember, it's one function f of x, and then you open this brace to write all the possible definitions. So every single time, one function, not two different ones, okay? So one function f of x, I see two different types of graphs. And what are my two graphs? I recognize the 1 over x function for all the x's less than 0. So for x is less than 0, I see the 1 over x function from above. And then for x is greater than or equal to 0, I see the square root function. Done. Okay. Simple. Let me give you another easy one. Okay. So again, try and turn off the video and try these equations yourself. So I gave you two different ones. So match it up with the above, and hopefully what you came up with is, it looks just like the cube root function up until x's that are less than or equal to 1. I'm including the 1 in the square root function. And then to the right of 1, so for x is greater than 1, it's simply the 1, 2, 3, y equals to 4. So it's the constant function y equals to 4. So horizontal line after that. Now, sometimes we might even write the word if. So 4x's. Sometimes we leave the if alone so that we don't get confused. For homework, I put if every single time. Just, yeah, if. You don't necessarily need to write if, but here I did write if every time. You can just write comma and then it's clear 4x's from here to there. But yes, hopefully you guys get an idea for this. Okay, so here are two wordy problems that translate into piecewise defined functions. So this is where the need of piecewise defined functions is coming from. It says, a museum charges $5 per person for a guided tour with a group of 1 to 9 people. So if you're coming with 1 to 9 people, it's going to be $5 per person. Or a fixed $50 fee for a group of 10 or more people. So if you bring 10 or more people, you basically just pay for 10 people, no matter how many more you bring. So write a function that relates n, the number of people, to the cost. So C of n is going to equal to, if you're bringing between 1 and 9 people, you're going to pay $5 per person. So for each person that you bring, you have to multiply that to 5, yes? So one person is 1 times 5. 2 people is 2 times 5, right? So $10 for 2 people. 5 per person, so times the number of persons. However, if n is greater than or equal to 10, you bring 10 or more people, there's a flat fee of $50, right? That's a constant function. It's going to be 50, anything after that. Okay. So let's see, what would be the cost of bringing in 3 people? Well, n is 3, n is a number between 1 and 9. I have to use the first part of the definition. So 5 times 3, it'll cost $15. What is the cost of bringing 13 people? Well, 13 is a number more than 10, so that cost is $50, right? Flat fee. Okay, so that's really when we use piecewise defined functions, when the definition or the rule that makes up this relation between two unknown quantities changes, yes? My two quantities are number of people and the cost, right? So we change the rule, and so it has two different types of definition depending on what n is. Here it is. A cell phone company uses the function below to determine the cost in dollars for G gigabytes of data transfer. So if the number of gigabytes is between 0 and 2, you pay a flat fee of $25. That's what that means. Okay. So if you transfer G gigabytes of data and G is between 0 and 2, you're going to pay $25. If you're going to transfer more than 2 gigabytes, basically what it says is you pay your $25 for the first 2, and really for everyone after that you're going to pay another $10 per gigabyte. So let's use this definition to find the cost of using 1.5 gigabytes. Now this number of gigabytes, as you see, is between 0 and 2, so the cost is simply $25. If you're going to use 4 gigabytes, then what is the cost of 4 gigabytes? Remember, we're using function notation. We're substituting G with 4. Now, we know that if G is more than 2, we're going to use the second part of the definition. So that's where I plug in my 4. And again, that's why we practiced last week a lot of evaluating expressions. You can put this easily in your calculators, or you can use the order of operations, hopefully properly. So you're paying really $25 for the first 2, as I said, for the first 2 gigabytes. And then for the next 2 gigabytes that take you to 4, you're paying $10 each, for a total of $45 cost. Okay, so that's how piecewise defined functions work. You have different definition for different parts of the number line. All right, this is it.